Good morning, all of you.
Morning, ma'am.
Today's resource person is Dr. P. Tamilarasan, scientist and ACSIR Assistant Professor in Electronics and Electrocatalysis Division from Central Electrochemical Research Institute, Karaikudi. He has completed his PhD from IIT Chennai and postdoctoral fellow from King Abdullah University of Science and Technology from Saudi Arabia. His main research areas are organic electrochemical transistors and in situ spectrochemistry, bioelectrochemical devices, and microbial electrochemical systems. He received many awards and recognitions. The best PhD thesis in energy applications from IIT Chennai in 2014, the invention of implantable glucose biosensor was widely recognized by the national media. Invention Award from the Intellectual Ventures USA, fellowship including UGC, CSIR, JRF, JSP, GATE, etc. He is a member in many areas like Society for Advancement of Electrochemical Science and Technology, member representative in Electrochemical Society USA to represent Chitri Karaikudi. He has published 24 papers in reputed journals, including Nature Materials, Small, JMCA, JPCC, etc. Filed a US patent on hydrocarbon production from carbon dioxide. He has given invited talks and presentations in more than 30 scientific events. As a project investigator, leading 3 sponsored projects and completed 1 sponsored project. As a member, he contributing to 1 industrial project. So we are happy to have a nice person for the presentation. Sir, we invite you for this session, sir.
Thank you, ma'am. Thank you, Dr. Swarna Lakshmi. And in this nice morning, I'm really happy to meet you all. I'm seeing more than almost 90 participants here. Really a good number indeed. So I'm just, ma'am, if you withdraw your presentation, I can upload mine. Yeah.
Yes, sir. You can upload.
So I guess you all see the.
Yes, sir. It's visible, sir.
Oh, fine. That's great. So as Dr. Swarna Lakshmi requested, it's going to be a 1.5 hour presentation. So I'll try to stick with my time. And this nice day, with a very good morning to all of you, I would like to discuss some of the aspects of an enhanced Raman spectroscopy, where nanotechnology is a strong tool to enhance the Raman spectroscopy. What is enhanced and why it has to be enhanced and how it is enhanced. All these things will be discussed in this presentation. I hope this will be useful for you. And mainly I will touch some aspects of the fundamentals and some applications. Finally, I will give some hint of challenges and opportunities of this field of research. And as Professor Swarna Lakshmi introduced me, I'm from Central Electrochemical Research Institute and affiliated to Electronics and Electrocatalysis Division. Basically, I work on spectroelectrochemistry that includes enhanced Raman spectroscopy. And my second field of research is on organic electrochemical transistors. And mainly I focus on biological applications like biosensing or understanding the biological process say stimulated conditions, and while there is a chemical or biological process, how to identify the intermediate states, intermediate levels, or intermediate species. All these things are my research interest, and I will not go much deep about the fundamentals, but it's better to start with the basics of Raman spectroscopy. Not too much, just I will touch upon. As we all know, Raman spectroscopy is a raw vibronic spectroscopy. In publications, you will simply listen that it's a vibrational spectroscopy, but it involves all the three electronic energy levels: electronic, vibrational, and rotational. That's why it's a raw vibronic. So when you excite your sample with a laser, actually the electronic transition happens between two electronic energy levels. So from here to here, and in those electronic levels, particularly, it goes from one particular vibration level to another vibration level. Even in that vibration level, it goes from one particular rotation level to another rotation level. So electronic spectroscopy is the UV visible, and vibrational spectroscopy is the IR spectroscopy, infrared spectroscopy, and the rotational spectroscopy is our microwave spectroscopy. So it covers all the three regions, but the electronic transition is not going to give any new information other than our UV visible spectroscopy. So we will not, Raman spectroscopy is not emphasized about the electronic transitions, and the rotational energy level transitions are actually a fine structure of a vibrational spectroscopy. When you see a Raman spectrum, they will talk about Stokes and anti-Stokes lines, but the rotational transitions are the fine structure of these Stokes and anti-Stokes lines. So it counts all the three electronic energy level transitions. Now, we also have another spectroscopy called IR spectroscopy. It simply talks about the vibrational energy level transitions, or what you're seeing somewhere here. Now, what is the difference between Raman? Why it is different from IR spectroscopy? Let's talk about the very classical. You might have heard a lot about the carbon dioxide molecule and its Raman activeness. When you take carbon dioxide molecule, it is all these symmetric stretchings are symmetric. All these symmetric stretchings are symmetric in electron cloud nature, so they are not active in a IR spectroscopy. For to make IR spectroscopy active, you have to have a net dipole moment change. That means change in net dipole moment. Why? It is because, according to the classical theory, the radiation is obtained only from an oscillating dipole, oscillating electric dipole. So if you want a radiation, you have to have, first of all, an electric dipole, and that should oscillate. That means there should be net change in dipole moment. That is, there should be net change in D. The D is nothing but the distance between the positive and negative charge of a dipole. So in that case, if you have a symmetric molecule, then there is no D. First of all, there is no dipole. If there is no dipole, then there is no IR activeness. All the asymmetric vibrations are IR active. But if you go for Raman spectroscopy, you no need to have a net change in dipole moment, even if you slightly disturb your electron cloud. That means if you slightly disturb the polarizability of your electron cloud, then the Raman signal will be activated. So that is the main advantage of Raman spectroscopy over IR spectroscopy. Now, if you see the probability of Raman transitions, as you know, Raman scattering is an inelastic scattering. While you send 10,000 to 10 lakh photons, only one photon will be scattered as a Raman photon. So rest of the photons will be Rayleigh scattered. That is an elastic scattering. And the Raman scattering is inelastic. Even in Raman scattering, there are two kinds. One is Stokes and another one is anti-Stokes. If the photon inelastically scattered, with the loss of energy, then it is called Stokes-Raman scattering. If the photon gains energy, then it is called anti-Stokes-Raman scattering. Fine, everything is fine. Now I said the probability of Raman scattering is 10 power minus 4 to 10 power minus 6. That means every one photon of 10,000 to 10 lakh photons will be scattered inelastically. This is very small. It is very difficult to get a signal from trace amount of sample. Even some of the samples with very low Raman scattering cross section, even for the bulk sample, you will not get Raman signals. What about a trace amount of samples? If you want to measure some biological molecule in your body fluid, then it will be of a very trace amount. It is very difficult to find this amount of samples in a given sample. So what can we do? We have to enhance the signal somehow. How to enhance? Let's see this equation. Mu is equal to the polarizability times of electric field. Now, the polarizability of mu is nothing but the degree of polarization, and the polarizability is an intrinsic quantity of every molecule. It is very specific to molecule, and it is so called. We don't have any control over this, but let's discuss about it later. And another one is electric field. So if you increase electric field, the degree of polarization will be increased. If the degree of polarization is increased, your net amount of Raman scattering will be increased. Now, let's take this equation. This is the intensity of Raman signal. It is proportional to the incident intensity. Incident intensity is nothing but electric field, because if you take a electromagnetic radiation, you will have two components: electric field component and magnetic field component. And if you want to, if you increase electric field component, obviously you will have a better Raman intensity. If you want to increase electric field component, then you have to increase intensity. Okay, because the energy of a single photon is proportional to its frequency. So it has nothing to do with amplitude. The amplitude is something to do with the intensity. So you have to increase intensity, but you cannot go on increase the intensity. At beyond certain level, there will be an ionization related problems. So, or heating related problems. So you cannot increase the intensity beyond certain level. In that case, we should not increase intensity of the incident light, that is I0, but we should increase electric field. This is one thing. Why we have to increase electric field? As I already said, the electric field is going to decide the Raman intensity. There is a relation here. The enhancement of the signal is proportional to the E square times of the electric field of the incident photon, that is square, the electric field square of the scattered photon. So if you consider that the incident and scattered, physically it will not be. Technically, if you are talking, incident and scattered will not be same. But since the change is very minimal, if you take approximately equal, then it is the enhancement factor is proportional to e power 4 times. So if you increase electric field, the enhancement in enhancement factor will be increased in power of 4. So this is I think this justifies why we have to increase electric field. Now, how to increase electric field? This is the main question now. So I'm sure you all would have heard about surface plasmon resonance. It is nothing but the collective oscillation of electron cloud of a metallic surface when the metallic surface is in an interface with a positive refractive index medium like air. Our metals are always a negative refractive index bodies, and if it is in interaction with a positive refractive index medium like water or air, then there will be a collective oscillation of electron cloud. Fine. And the propagation of these surface plasmons starts at the point where the photon hits the surface, and the amplitude will gradually go down, and it will diminish at a certain point. The complete length is called propagation length. And there is another phenomena called the LSPR, the localized surface plasmon resonance. This is nothing but you have the surface plasmon having the finite length, right? Finite propagation length. If you reduce the particle size or the surface size less than its propagation length, then this propagation will not go to the end till it is diminishing. So it will be confined. So if you confine it, what will happen is at the point where the photon hits, you will get enormous amount of electric field enhancement. So this electric field enhancement can be definitely used for Raman spectroscopy. This is the key point in surface enhanced Raman spectroscopy. And what will happen? Okay, you have taken a metallic particle and you have reduced its size into nanoparticle size, say to the size smaller than its SPR propagation length, and you have illuminated with light. So now it produced LSPR on its surface and it produced a large electric field. What if you put two particles together, adjacent to each other? Then there will be some other phenomenon called LSPR coupling. These two LSPRs of the particles will couple together and will form an enhanced electric field region of nanometer cube size. So the region between the two particles will have a very high field enhancement. Like if you calculate this theoretically, it is going up to 10 power 15, and experimentally people have observed up to 10 power 8 to 10 power 10 times the enhancement factor. And also the enhancement factor is depending on the direction of the light with respect to the particle's orientation. For example, if you have a particle on another particle and you are illuminating from the top, then what will happen? The electric field enhancement in this coupling region will not be too high, it will be very less. There will be a diminishing effect here. But if you send the radiation from the side, then you will have a large enhancement in this coupling region, and this coupling region is called hotspots, sets hotspots. Okay? And as I said here, the perpendicular component of the light, that means when you pass a light, your electric and magnetic field components will be perpendicular to the light direction. So only the perpendicular component will be enhanced. So that's why when you form a set substrate, you have to form a kind of monolayer distribution or self-assembled monolayer kind of stuff. So that is a hint for us. And I just wanted to touch a little bit of history about surface enhanced Raman spectroscopy. In 1970s, from University of Southampton, a group of scientists were studying the metal organic interactions using Raman spectroscopy. The group includes Fleischmann and Professor Handra and Professor McLean. And in 74, they were studying the nature of pyridine on roughened silver. And they found that the Raman signal of pyridine was enhanced enormously up to 10 power 4, 10 power 5 times. So they attributed this simply to the high surface area of silver. Because silver is roughened, because of this roughness, the silver got high surface area and it accommodated high number of pyridine. And 3 years later, from University of Northwestern, Professor Van Duyn's group relooked into this phenomena. They thought that it is the 10 power 4 to 10 power 5 times, or nothing but almost 1 lakh time enhancement cannot be because of simply the high surface area of silver. Why? Because the silver surface area would be increased more, not more than 100 or 200 times. But how it can go 10 power 4, 10 power 5 times? So they thought it is something beyond the high surface area. And they have proposed the electromagnetic enhancement mechanism, what we have seen already, the LSPR and the LSPR coupling, and all these things have been proposed by Professor Van Duyn. And I cordially wanted to dedicate this presentation to Professor Richard Van Duyn, who expired last year in July 28th. And he contributed a lot for this field, and he has advanced this field a lot. And apart from his electromagnetic enhancement mechanism, there was also another mechanism called chemical mechanism that I will explain in the next slide. It was proposed by Albridge and Creighton from USA. And as I already said, the polarizable the degree of polarization is proportional to your polarizability and electric field. The electric field is something to do with the electromagnetic mechanism, what was proposed by Van Wyn, and the polarizability is something to do with the chemical mechanism, what was proposed by Creighton group. And about the chemical mechanism. Here is the polarizability. This polarizability is, it depends on the electron cloud. If you have bigger electron cloud, then you will have more scattering, then you will have more polarizability. Or if you have a higher electron density, like you have some lone pair electron, like nitrogen is there, then you will have more scattering. And thirdly, the third possibility is injection of charges from outside. If you inject charge to a molecule, then you are increasing the net charge density of a molecule. Then you will once again increase the polarizability. So these are the three possible. The third one is belongs to the chemical enhancement mechanism. And there also there are proposing two different mechanisms. One is the charge transfer mechanism, where the metal surface, the plasmonic surface, and the molecule are in contact. And the metal surface transfers an electron to the molecule, and later it will be compensated by the molecule here. So this is charge transfer mechanism. And secondly, they are also proposing a metal complex formation mechanism, where the metal and molecule forms a complex, and because of that, the excitation is assisted. Generally, as we have already seen, the electromagnetic enhancement mechanism will practically go up to 10 power 10 times enhancement, and the chemical enhancement will go up to 10 power 2 times enhancement in the Raman signal. Before designing a set substrate, we should know how the set substrate should be. And there are some basic principles, and there are basic needs that we will see here. So let's just take a particle. As I already told, take a spherical particle, and you just illuminate with some light. It will produce electromagnetic field around, and because of that, it will have high electric field. Okay? And if you put two plasmonic particles together, there will be an LSPR coupling here, and this region is called LSPR coupled region or hotspot. And how far these two should be separated? So can it be touching each other? They are touching each other. There is no LSPR coupling, because there is no LSPR first of all, because the surface plasmons will propagate from this particle to this particle, so there is no confinement. So ultimately you have to separate them. How far we can separate? Here they have taken 100 nanometer sized particles, and they studied the electric the enhancement factor with the separation, interparticle separation. They started from almost I think 20 or 30 nanometer distance and went up to 150. You are seeing an exponentially decaying function. So while you separate the particle too much away, then the enhancement factor will fall exponentially. So you have to have an optimized separation between two particles. And secondly, there should be a sharp edge. Sharp edge means the more confinement. So if the radius of curvature of this surface is more, then you are confining the LSPR more. I mean SPR more, and you are producing much stronger LSPR. That means a sharper edges will produce very high electric field, right? So let's take these three structures. One is the nanowire structure. It's a silver nanowire. They have simulated this with a simulation tool, and what you are seeing here is actually the light is passed from the top. Just assume that the light is passed from the top. When it is passed in this direction, you will have electric field in this direction. That's what you are seeing here. Electric field vector is in the horizontal direction. So because of that, you got a very high field in this more curved surface, and there is no very less field enhancement here. And this field enhancement is also not because of the coordinate along the tube axis. It is the coordinate in the tangential direction. The confinement was in the tangential direction. So you are getting very weak field here. In case if you have applied the light from the side, and if you produced the electric field vector upward, then you would have seen a very large field somewhere here. Okay? And similarly for the spherical particle, obviously because of the less radius of curvature, they got very weak field. And for the triangle, it's indeed like a prism. You are seeing like a triangle. Since the electric field component is perpendicular to its direction, so these two corners have produced enormously very high electric field in the localized region. So when compared to this enhancement, this would be much higher, several orders of higher enhancement. And so I guess you understood that the radius of curvature matters here, and the direction is also matters here. Direction of the light is also matters here. And I was talking about the nano gap. The gap between the two particles is important. There was another study that has simulated the importance of a nano gap between the surface. What they have done is they took a probe with a particle at the edge, a spherical particle at the edge, and they also took a plasmonic surface. And the first figure is the system with nano gap, I think 2 nanometer gap, and the second one has no gap. And from the picture, you will simply think that this one is more brighter and it is giving more electric field, but it is not true. You have to see the scale here. The scale is 1875, and here the scale is just 5.3. And the brighter regions are just giving 5 to 6 enhancement, but the brighter regions here, whatever you are seeing here, will give you more than 1800 times enhancement. And also you can see this graph. They have simulated the similar studies for different refractive indexes for the vacuum at 1, and also they put some other medium, and they have simulated it, and you can see for all the medium, the nano gap structure gives you more enhancement compared to the non-gap mode. It's nano gap, it's non-gap, so you have to distinguish between these two. And having this kind of idea, people have developed several substrates like a self-assembled monolayer of nanoparticles. They have also went with some template-assisted patterns using anodized alumina, and they also went for electron beam lithography to create some array of nano features. And all these are created to get a well-defined nano gap systems. And okay, if you create all these systems, is it all solved? No, it is certainly not. Why? Because let's see the hotspot produced between two particles. If you see this region, when this is the lowest distance between the two particles, where you have the highest enhancement factor, because already we have seen the interparticle separation will exponentially drop the enhancement factor. So at the lowest distance, it has very high field, like 10 power 8. When it is going radial out from this point, then you are losing the enhancement factor quite rapidly. So it is, as I already said, it drops in an exponentially decaying function. So even if you have a well-defined system, then if you put a molecule here, that will produce a more stronger signal than putting a molecule here. So this is a very big limitation in CERS-related CERS-based studies, and we have a very good solution for that that I will discuss in the later slides. And first, we will see some of the aspects of the CERS substrate fabrication. Generally, the CERS substrates are fabricated in 3 different methods: the chemical method, physical method, and electrochemical method. In chemical method, they will simply take a metallic salt and they reduce it in controlled manner. So the metallic salt will be formed as a metallic nanoparticle. A colloidal dispersion will be obtained, and this colloidal dispersion will have different shapes like sphere, rod, or cubes, and so on. And these structures will be deposited on some CERS substrate or some substrate. Here they have used filter paper. Generally, they will use silicon wafer, and then we can go for CERS analysis. Now, there is also another method using Langmuir blot gate. where you will functionalize the molecules with, functionalize the nanoparticles with some say surfactant molecules, and you will form a film over the surface of water, and then you can pull this film on a substrate using Langmuir blotted film formation. So this also will give you a very good SAM layer, self-assembled monolayer. And apart from this colloidal dispersion method, there is also some physical method and electrochemical method. These two are interlinked indeed. If you see this one, these two images are coming from derived from nano imprinting technology, and these two are by Nanosphere Lithography, and this is once again some physical vapor deposition growth method. Let's go with one by one. First, about the Nanosphere Lithography. We already know we need a very high surface homogeneity. Even if you have very high surface homogeneity, there will be a heterogeneity between those two particles. So we have to keep that in mind. Keeping that in mind, we will discuss these techniques. And of course, the ultimate aim is to get more surface homogeneity. And the substrate fabrication method will definitely play a major role in this surface homogeneity. In the Nanosphere Lithography, they take a substrate and they put some template like polystyrene nanoparticles, or sometimes silica nanoparticles. They form a self-assembled monolayer, and then they deposit a metallic film over this. If you simply deposit a metallic film by physical vapor deposition, you will see something like this structure. And if you lift up these particles out, these templates out, then you will see a very well-defined patterns, like it's a nano pyramid-like patterns. So these are very well distributed, and at a particular area, you will know the number of features inside. So this will give you an opportunity to back calculate the possible enhancement corresponding to the number of particles. And in the electrochemical deposition, once again they have lifted off. So you are seeing something like a honeycomb lattice. So all these black spots are the place where you had the template. This is Nanosphere Lithography. It's a very simple one, which can be tried without any sophisticated facilities, particularly the electrochemical one. And second one is they use, this is a template assisted method. Another template assisted method is there where they use anodized alumina. They took a substrate with graphene, and they put graphene is optional. They just used graphene for their purpose, but the technology doesn't require graphene mandatorily. So optionally you put graphene and put anodized alumina and deposit gold film. So while you lift off the anodized alumina, you will get a very good array of the gold nanoparticles arranged in a surface. So here, this is what you are seeing. This is the anodized alumina surface, the same image of anodized alumina, and here what you are seeing is the particle distribution after deposition and lift off. And I'm sure you all will agree that nature is the very good nanotechnologies. So it produces a lot of nanoscale features with very high symmetry. And one of that kind is the Lotus leaf. I'm sure you would have heard about the Lotus leaf effect, because a Lotus leaf, the water will not stick with the Lotus leaf because of its structural structural hydrophobicity. The nanoscale pillars on the surface of Lotus leaf produces a negative contact angle. Because of that, it will not, the water will not stick on the leaf. The similar pattern is existing on the fly's wing. It's a kind of fly, and its wing has some nanoscale features like pillars. So this is what the same image of the pillar, and the same thing you are seeing here from the top view. And if you deposit gold on this surface, then you will actually produce gold fingers, isn't it? It is templated by some organic molecule, and you will produce gold fingers. And if you increase the deposition time, gradually the gap between two pillars is gradually increasing here. So you just see these three images. When compared to this image here, the gap between two pillars is pretty much reduced. And in this way, you can control the gap between the nanoscale features. This is what we have discussed. The gap between a nanoscale feature matters a lot in sets, and that can be easily controlled by this method. And to emphasize with the nanofabrication related stuff, nanofabrication related set substrate fabrication. Here you are seeing some nano patterned structures, and this is an amazing result. They have created features of different structures which we are seeing every day, like moon arc and moon arc face and cube, square, and all these things have been fabricated using e-beam lithography, photolithography followed by e-beam deposition. And similarly, they have produced nano pillars and some well-aligned nanostructures using nano imprinting. And here you are seeing the e-beam lithography based patterns. All these have been produced towards set substrate applications. And once again, I wanted to touch the point that we have to have a very very clear separation between these two particles. That is, we have to create a nano gap. And this study by Professor Ziqiu Tian from Xiamen University, China, they have developed a special substrate for sets analysis. It's called SHINE, self-isolated, shell-isolated nanostructure. So SHINE gives the new field of research called SHINERS, cell-isolated nanoparticle enhanced Raman spectroscopy. So the substrate is very simple. You have metallic nanoparticles, and you just coat a thin layer of non-metallic or inert shell over that. So what will happen? Even if you put the particles together, and even if they are touching each other, the metallic surfaces are not touching each other, so they are well separated. In that case, you can, if you by controlling the shell thickness, you can control the gap between the two particles, right? So in this way, they produced the set substrate, and they have demonstrated the in situ measurement of some species formation. For example, here, if you take this fourth curve, this is the PT111 substrate, where there is a PTH formation, hydrogenation. I mean, because of the hydrogenation, there should be a PTH formation, and there should be PTH vibration mode in Raman spectrum, but it was not observed in normal Raman spectroscopy. And even if you put a SHINERS particle with very thick layer, like 20 nanometer, you are seeing in this image, you are seeing 20 nanometer thick layer. If you put this layer on this substrate, you will you are not seeing anything, because the interparticle distance is too much. So the electric field enhancement is completely diminished between this 40 nanometer gap between the two particles, because each particle will have 20 nanometer shell. And if you go these three curves from top to bottom at different potentials, you are seeing the clear PTH vibration peak in Raman spectrum, while you put a nanoparticle with just 2 nanometer shell. Means while you reduce the shell, you are start seeing the features. So it actually enhances when you reduce the shell thickness. And the similar thing was demonstrated with alumina. The first study was with silica. The second study is demonstrated with alumina layer, and the same pattern with the increase in potential, you are seeing increase in peak intensity. And they have also demonstrated an application for this study. They wanted to find out the presence of methyl parathion, it's a pesticide, on orange. So they took a Raman spectrum of orange, and they took a Raman spectrum of methyl parathion also. So methyl parathion gives a peak somewhere 1346. If you have methyl parathion on the surface of orange, then you will expect a peak here. But in normal Raman spectroscopy, it was not observed. Only when you put a SHINERS particle, you are observing this peak. So this is the potential of this technology, and they have extended the application of this substrate to other work also. Like they observed the in situ chemical reaction using this substrate. What they have done is they took carbon monoxide, they oxidized it into carbon dioxide on a PTFE substrate. So what will happen if you oxidize it? Then you have to see the transformation from carbon monoxide to carbon dioxide. So just see this curve here on PTFE. People may have claimed that the SiO2 plays a major role here, because SiO2 layer gives you an interference effect. Because of that interference effect, you will get slight enhancement in Raman signal. But indeed, it is not true. If you put only SiO2, there was no peak here. Or it may be people would have claimed it may be because of the presence of Fe. No, it is not, because if you remove Fe, then once again you didn't get any peak here. Or people would have claimed that it is the peak from the particles, the shine particles. The shine particles also shows no peak here. And when you put both the PTFE and shine particle, and if you allow carbon monoxide and oxygen, then it gives you a very strong peak here, that is corresponding to PTC formation. And this is one of the in situ tests they have done with this shyness substrate. And another application for this shyness substrate is on in situ battery analysis. What they have done is they made an in situ spectro-electrochemical setup, where you have access to the anode through the spacer, the lithium foil, and the separator. So you can directly access this NMC composite electrode. And if you just see here, you are seeing the NMC 811 catalyst, its surface and the bulk characteristic, and also they have given the electrolyte. So keeping these three as a reference, they just went with the OCV up to 4.8 volt scan, potential scan. So they have observed a gradual increase in peak at this region. Okay, and this peak is corresponding to the formation of cobalt oxide and nickel oxide formation. The cobalt oxide is a spinel structure, and the nickel oxide is a rock salt structure, and the formation is observed here for NMC 811 catalyst. But for NMC 111 catalyst, this formation is pretty much controlled here. So the peak intensity is the relative intensity of this peak is not quite high compared to the NMC 811. So the conclusion is, compared to 811, the 111 catalyst is much better in terms of COO3 NiO formation. Yes, the COO3 NiO like oxide formation diminishes the performance of the catalyst. And after this shyness related applications, I just wanted to get back to CERS, where I will just emphasize with some of the applications. The first one is the whole cell CERS. That means when you have a cell, a living cell, you can take a CERS spectrum of the cell and CERS spectrum of the components inside the cell. For example, let's take the breast cancer cell lines. They took two cell lines, and they wanted to distinguish these two cell lines based on Raman spectroscopy. And how to do that? What is the big difference between these two cell lines? And they found that the UPAR and EGFR markers are different. These two cell lines will have different ratio of these two markers. Okay, so that we have to identify here. What they have done is, they took a plasmonic nanoparticle, they put some Raman reporter like NTP or DADT, and then to make this structure biocompatible, they capped it with the TEPSA and MPEG saline, and then they attached the peptide corresponding to UPAR or EGFR. So now this particle is ready to attach with any presence of UPAR or EGFR, right? Now what they have done is they give this the mixture of this two nanostructures, which gives the Raman spectrum something like this, where you will see the features related to the EGFR probe and the UPAR probe. Okay, they mixed it and they gave to a living cell, and then they mapped the Raman spectrum of the complete cell. Now you are seeing the distribution of EGFR reporter and UPAR reporter, right? If you combine these two, you will get this image. Similarly, for MDA or MCF cell lines, they have given the same mixture. Now for the MDA, you are getting more of this UPAR more of UPAR related marker compared to EGFR marker. But for MCF, the almost in the picture it looks almost same, but the EGFR probe is more intense here compared to UPAR, and they have made a ratio of these two, and they found that for MDA cell line, the UPAR to EGFR ratio is 1.8, and for the MCF cell line, the ratio is 0.48. So in the future, if you do any analysis, if you have any cell line, if you do Raman spectroscopy, and if you find that the UPAR is more in that cell line, then you can simply tell that it is an MDA cell line. And if the EGFR is more, then you can tell that it is MCF cell line. So this is one of the application of cells. It's called cold cell cells. The second application in biological industry is the detection of an antigen corresponding to hepatitis B. It's an immunosensor, as you know, because you have used antibody here. What they have done is they wanted to identify the presence of antigen corresponding to hepatitis B virus. So they produced a substrate where you have a silver silver thin film, silver or gold thin film. On that they attached some linker, like aminopexine thiol like linker, and then on the top they have attached the antibody using EDC NHS chemistry, and the rest of the spaces and unsaturated linkers are masked with bovine serum albumin. The substrate is ready, and then for the sandwich type immunosensor, they also have to produce a reporter. So the reporter is produced something like this. They took a gold nanoparticle and then they attached some linker. On that linker, they put a Raman reporter like a fusion. And along with fusion, they also have attached the antibody with the EDC-NHS chemistry. Now, as I already said, it's a sandwich type. So first, you will have the substrate here and the reporters here, and you will put your body fluid here. The body fluid will flow through the reporter region, where if there is any antigen, then it will pick up the reporter. Then it will flow further through the channel. When it reaches the substrate, if there is any antigen that is attached to reporter, then the reporter and antigen will attach to the antibody in the substrate. So here is the antibody in the substrate, and you have antigen, and once again the antibody in the reporter. So all these things will be on the substrate. Now, if you wash out whatever the reporter you have without any antigen will be washed out. Only these sandwiches will remain in the substrate. Now, if you do Raman spectroscopy, then you will be able to identify the presence of fusion. So that's what you are seeing here. If there is no antigen corresponding to hepatitis B, then you will see a Raman spectrum something like this, which is corresponding to the presence of native organic stuffs like bovine serum albumin and so on, other antibody and so on. But if you have any antigen, then definitely your fusion will be present here. So you will see a strong peaks corresponding to fusion. So in this method, you can get the detection level as low as 0.01 international unit per ml with a very good RSD value of 10%, less than 10%. And another application for this CES substrate is single molecule detection. Detecting a single molecule and probing its response to a simulated environment is very important, because to understand the nanoscopic world or microscopic world, we have to understand an isolated systems. So isolated single molecule has to be identified, and you have to probe it in a particular time scale. Okay? So as I already said, the CES substrate gives you a signal enhancement up to 10 power 8 times. So since you have a 10 power 8 time enhancement, and if your molecules, if you just assume that your molecule has Raman scattering cross section of 10 power minus 24 or 25, like Rhodaman G, then if you put this 10 power 8 together, then you will come to 10 power minus 15 to 10 power minus 16 region, which is quite sufficient for an optical analysis like you used to do. Because the optical analysis will have scattering cross section of 10 power 14, 10 power 15 in that region. So you can bring the Raman scattering cross section all the way to an optical scattering cross section region using CES substrate. So that's what they have done here. In 1997, from Professor Emory's group, have identified a single Rhodaman 6G molecule on a metallic substrate using single molecule CES. In fact, they used CES. Later, they named it as a single molecule CES. What they have done is they put a molecule on a substrate where they have silver nanoparticles, and when the molecule is at the hotspot, then you will get a Raman spectrum corresponding to that single molecule. And there are some ways to identify whether you are probing single molecule or multiple molecule, that I will come back on later slide. First of all, they have just mapped the whole region, and they took a line like this. So if you go from the line A, then you are seeing some peaks like this. But while you are going from line B, you are seeing a very strong peak, something like this. This is corresponding to the Raman spectrum of the intensity is corresponding to the CES enhancement. And there is also another way to push the single molecule towards the CES substrate, because for a single molecule analysis, they use always picomolar or femtomolar solutions of any Raman molecule, Raman probe molecule like Rhodaman 6G. But pushing the molecule into the hotspot is very difficult. So for that, they have used Magnoni convection, where the surface tension of two different structures will play a role. So what they have done is they took a metallic nanoparticle substrate, and then they put a SiO2 microsphere on that. Because of the surface tension gradients, the molecules were pushed into the hotspot. And in this manner, in this method, they got the enhancement factor up to 10 power 10 times. And here is another application, probing a single molecule. Already we have seen a single molecule is identified by CES. Now the group from Australia have Professor Eric's group from Australia. They have actually probed the complete electrochemical reaction of a single molecule. What they have then done is they took a CES substrate and they arranged all these spectro-electrochemical setup, and they scanned from minus 0.54 to minus 0.07 volt. It's just a cyclic voltammogram. When they scan it, they got a CV of something like this. Okay, this is for the bulk. For the bulk, what you are saying is two different peaks here. Both are very broad peaks. Okay, and it has its own very broadness, and it has its own full width half maxima. But does it mean that a molecule is gradually oxidizing and reducing? It is not. It is a cumulative ensemble effect. Each molecule will have its own very sharp oxidation and reduction potential based on its environment. That they have proved with this method. If let's see here, if you are seeing the stress intensity here with the time, and with time you are also seeing changing potential. If you have multi molecule event, then you will have a very broad spectrum, something like this. Okay? But if you have a single molecule event, then there will be a very sharp increase and very sharp fall, something like this. So this tells you whether you are probing a single molecule or multiple molecule ensembles. Okay? And if you identify a single molecule event, then you can do electrochemistry for that single molecule event. That's what you are seeing here. For these 4 molecules, so you are seeing 4 different oxidation and reduction. These for all these 4 are very sharp in nature. Okay, they are not like broad, something like this. So this complete analysis tells that whatever you are seeing here is an collective information of an ensemble, not for the single molecule. Each single molecule will behave very precisely based on its environment. And another application for sets is you can probe in situ electrochemical oxidation reduction of polymer. They took hydroxylated PDOT. For a hydroxylated PDOT in its reduced form, you will have strong Raman peak, but while you oxidize, the peak intensity will go down. Okay, this is a Raman feature. So they took this property, and they have scanned the potential from 0 to minus 0.52 plus 0.5. While they go the complete window, it goes up and down like a wavy nature. This may be because of the Fermi level tuning in the substrate, because there is a possibility if you tune the Fermi level, then obviously you will tune the Raman intensity. So to confirm that it is not because of Fermi level tuning, it is because of oxidation and reduction. They also took MBA, mercaptobenzoic acid, and where they have scanned it from some 0 to 0.5, where there will be no oxidation and reduction for this molecule, and they found it there is no change in peak intensity. That means the whatever the wavy nature you are seeing here is not because of Fermi level tuning, it's because of oxidation and reduction. So having this proof, they employed this for initially they took a reduced form of hydroxylated PDOT, and they put some oxidizing agent, then it is oxidized. Because of this oxidation, the degree of oxidation, the peak intensity is reduced. The peak intensity is reduced here, and once again they have regenerated with electric signal, and they used the same substrate for identifying another oxidant like APS. You are seeing the same effect here, the drop in peak intensity, regenerate with electric signal, and once again use it for some other oxidizing agent. So in this case, you can use the same film several times for several different oxidizing agents, and not only for oxidizing agent, instead of electric field regeneration by reduction, you can use this this reduction stage for identifying some other reducing agents. So this is the direct application. And excuse me if I can just drink a couple of sip of water. And all right. So already we have seen a technology called SEPS, surface enhanced Raman spectroscopy, and where we have seen how the surface enhances Raman spectrum and what are its applications. And we have discussed a lot about its surface heterogeneity in SEPS analysis. And also, if you put a SEPS substrate with a 10 nanometer particle, then your lateral resolution cannot be more than 10 nanometer, right? So in that case, obviously, you are losing lateral information or lateral resolution. And already we know the SEPS surface has enhancement factor up to 10 times. So we have already demonstrated it has capability to identify a single molecule and probe its monitor its electrochemical events throughout a reaction. Everything is fine, so you will get a lot of chemical information from CERS analysis, but we are lacking with the lateral resolution. So if you have a substrate, if you wanted to scan a 100 square micron substrate, then it is not possible with the CERS because the particle sizes are very limited, like it will be 10 nanometer or so. So in that case, if you want to get a better lateral resolution, we have to have some other technology. So it is a derivative of CERS. There is no big difference in the physics of signal enhancement, but it is only the difference in the device architecture, okay, or the substrate architecture. I'll explain why, and I'll explain what. It's just to take this image. Already I have explained this one. Professor Eric has published this one, where I said from the core of the hotspot, if you go out radially, then you will lose the enhancement factor exponentially, right? And we said that it is a big limitation, and we have to take a lot of care to account this. But in fact, it is not a big limitation. It's a big opportunity while you are considering tip enhanced Raman spectroscopy. It's called TERS, TERS. Why? Because in TERS you need a lateral resolution. The lateral resolution depends on the particle size. Okay. If you have a 10 nanometer particle, then in CERS the resolution is only 10 nanometer. But in TERS, it is less than that. Why? Because the enhancement here is not equal to here. So whatever when you are going from one point to other point, each point of the scanning matrix will have the will be given as same opportunity to experience the same electric field, right? So in that case, the other adjacent points will not interfere much with this point. Say, for example, you're scanning every 1 nanometer. So your 1 nanometer spot will be here, and the adjacent point will be 1 nanometer away somewhere here and here. So these two are in almost at least 2 orders of less enhancement, electric field enhancement compared to this. Because of that, the interference from other matrix will be very less. So this can be taken as an advantage, and they have developed a new technology called TERS. And why we need TERS, first of all? And as I already said, the surface enhanced Raman spectroscopy gives chemical information, and it lacks the surface lateral information. And if you see the other techniques like XPS, UV visible, and CERS, and other Raman techniques, derivatives of Raman techniques, all these will give you a very good chemical information, but not lateral information, as I already discussed. But if you see other analysis like SEM, TIM, and STROM, and so on, they will give you a very good lateral resolution, but there will be no chemical information, first of all. Maximum what you will get from EDAS is you will get the distribution of elements on the surface. That is the maximum chemical information you can get. If I have on a substrate, if I have say two different organic molecules like rhodamine and crystal violet, you cannot distinguish with CM or any other microscopy. So in that case, TERS gives you both the information. So that is the big advantage of TERS. We'll see some of the configuration related information here. TERS obviously will have a tip, a plasmonic tip, and the plasmonic tip will have a very sharp edge, and you will send the incident light, and you will get the scattered light. And there is also two different geometries called reflection geometry and transmission geometry. That's what you are seeing here. Based on all these configuration and all these techniques, we can classify the TERS analysis into 4 major configurations. One is the transmission geometry, where your tip and the Raman objective will be opposite to each other. So you will do it in a transmission mode. and you will send the laser from here, and it will transmit through the substrate, and here you will have the sample, which will be enhanced by this tip, and you will get the Raman signal back. This is quite efficient, but quite complicated in terms of instrumentation. And the second one is the side illumination geometry, where the tip will be on the top. So it will be a right angle to your substrate, and you will illuminate the tip with 90 degrees. This has two main drawbacks. One is the objectives at 45 degrees is not a very common configuration you will see in instruments. So this is one thing, and second thing is, whatever the scattering you will get, the maximum scattered photons will go in this direction. So the collection efficiency will be very less. The only advantage for this configuration is you can use a normal AFM tip, because in the normal AFM tip, the tip will be under the cantilever. You will have a cantilever, and underneath you will have the pyramid-like tip. So you can use those tips with a simple metal coating for this configuration, but it is not quite common. And the third one is, once again, it is a quasi transmission mode geometry only. You will have transmission from here, but you will have arc mirrors to focus from both the sides. So in this way, you will enhance the signal strength. And the more common test setup is this one. You will have a top illumination, and you will have a 45-degree tip. So this is very common, and even you can use a normal Raman spectrometer. If you have a scanning stage, just create a probe and put it in the Raman spot, then you will get test enhancement. So here I'm just showing some of the test tips already published in Faraday discussion. This is a silver nano wire. You are seeing very sharp nano wire with some of the nanoparticles on the top. You are seeing single nanoparticle, 2 nanoparticles, and more than 2 nanoparticles here. This is actually coated with a lot of nanoparticles, but these the nanoparticle on the tip will do the test enhancement. And there is a way to fabricate these tips. I'm just going to explain only 3 of the chip fabrication technologies. For the first one is electrochemical etching, where you will have a platinum ring, counter electrode, and reference electrode. You will have the silver wire working electrode. The silver wire is going to be sharpened, right? So while you are putting on the just on the surface of the electrolyte, and if you are slowly etching it, then you also have to slowly pull it. Then you will get a very sharp tip, something like this. It's a silver wire sharpened to nanometer scale. And then there is another way, like as I already said, if you wanted to go with the second configuration, you can simply use an AFM tip or nano indentation tip, something like this. Take this tip and coat with some metal thin film. Then you'll get a plasmonic enhancement tips. The third one is thermal or laser cooling. What they will do is they will simply take a micron-sized silver wire, and they heat the local spot with heat or laser spot. And because of the heat, the wire will be melted down. While it is melting down, they pull it away. Because of the pulling, because of the surface tension of this metallic melt, it will form a sharp tip. And since these wires are in micron size, they don't have mechanical stability, so they support these tips with glass, like glass capillaries. They'll put it in a glass capillary, and then they melt it along with the glass capillary. So finally, you will get a sharp silver needle coming out from the glass tip. And you are seeing a photograph of this. So then it's a magnified photograph, and you are seeing a SEM image of the tip. Using these tips, they have resolved, as I already said, surface enhanced Raman spectroscopy has a very good capability to give chemical information, but not lateral surface resolution. That a test should give that. In this work, they have distinguished two different porphyrins. One porphyrin has a metallic center, another one has a free base center. So they have coated a thin film of both of these, like a metallic center and free base center, and they also forms a very clear interface between these two. You see this one. This is the and these two porphyrins has its own corresponding common spectrum. Just the blue one is the metallic center, and the green one is the free base center. So they have mapped the interface with AFM. You can clearly see the interface, and it is the magnified region. And for the same region, they have also mapped the chemical information using TERS. What you are seeing is very clear interface between the two porphyrins. You are seeing blue, red, and green, pink. So this is what I was saying about the chemical information with good lateral resolution. And the same thing. So what we are seeing here is an intermolecule resolution. So it is capable of distinguishing two different molecules on the same surface. But it is not the maximum capacity of TERS. You can even go beyond this. In the same study, they have mapped a plane where you have the same molecule, and they could even go intramolecular or submolecular level resolution. For example, if you take the metal base porphyrin, you have metallic center and you have organic lobes. They have simulated the Raman spectrum of the molecular lobes and metallic molecular core, and they also identified the Raman spectrum experimentally for the lobes and the core. You can clearly see they are matching very well. Means the tests can go not only up to the intermolecular resolution, it can also go for an intramolecular resolution with the resolution of 0.4 nanometer. It can even distinguish molecular subunits, or even you can use it for specific site binding related studies. And a similar study with copper phthalocyanine also has been done for a single molecule resolution. They have formed a thin film of copper phthalocyanine, and you can see here the test mapping. And if you just map with the molecular structure, it's saying that each spot, whatever you are seeing here, is a single molecule. Okay? And they also did a study with the engaging and retracting related one. So while you are engaging, you will get more peaks. While you are retracting, you will get less peaks. If you take the difference between these two, you will get the exact spectrum corresponding to the copper phthalocyanine. So using this copper phthalocyanine spectrum, they have back calculated the scattering cross section. Instead of being 10 power minus 30, the scattering cross section has been increased 4 orders to 10 power minus 26 here. So in this, using this method, you can actually go for an intramolecular orientation, intramolecular site-specific findings, or intramolecular site-specific electrochemical reactions can be possible. Another application here, it is once again done by Professor Van Duyn, who invented sets effect. Here, what they have done is they took Nile blue in oxidized and reduced form. In oxidized and reduced form, Nile blue gives you two different spectrum, as we have seen in hydroxylated PDOT. So they have tested this with both the TERS and SERS. Okay? So in TERS and SERS, you will see clearly almost a similar spectrum for oxidized form, but while you reduce, there is some difference that I'll discuss here. Like if you take this molecule, Nile blue, it will have benzene ring as well as pyridine ring. Okay, so these two ring structures will have a different peak in Raman spectrum. If you see here, so whatever you are seeing here at different potential at 300 millivolt, you are seeing two peaks, right? While you increase the potential to minus 700 millivolt, then this peak starts diminishing. This peak is corresponding, this peak means the 1592 is corresponding to the pyridine ring. So when you increase the potential from, when you change the potential from 300 to minus 700, then you are actually protonating the pyridine ring. So you will lose the signal of signal corresponding to pyridine ring. And this is observed with the TERS, but using XERS, you are not seeing such kind of features. You are seeing even for 300 or minus 700, you are seeing almost the same structure for all these potentials. So this is the potential of TERS. So this is the potential of TERS on intramolecular or intermolecular resolution related studies. And after touching all these sets and TERS related topics, I think it's not fair to leave a topic called GERS, graphene enhanced Raman spectroscopy, because you all know graphene is a fascinating material, and it is a two-dimensional allotrope of carbon with an hexagonal cuneiform lattice, and it also has several potential. Out of that, one is the GERS, graphene enhanced Raman spectroscopy. And as I already said, there are two enhancement possible with Raman enhancement. In sets, you will see two components like the chemical enhancement and electromagnetic enhancement. With GERS, you will get only chemical enhancement, where the charge transfer is the mechanism. There will be no plasmonic enhancement. And to prove this, there was a lot of questions why graphene has to enhance the Raman signal. Of course, the enhancement is very less, like 10 power 2 times only, but still they have tried in several ways to prove that it is a chemical enhancement. In the first way, they put actually, if you see the Raman intensity as a function of concentration, it has to have a linear regression, right? But while you put several layers of molecules, it didn't follow the linear regression. It follows this trend. That means then the enhancement, the signal enhancement is not proportional. It's proportional, but it's not linearly proportional to the concentration. It means the molecules which are in contact with graphene only enhances, gets its Raman signal enhanced, but the molecules on the top are not getting enhanced. Similarly, they have taken a single molecule, and when the molecule is oriented differently, it gives different Raman signal. When it is vertically aligned, that means the charge transfer site is not in contact with graphene. You are getting a poor signal. When it is in contact, you are getting short signal. That means if the charge transfer site is in contact with graphene, there is a possibility of charge transfer, and because of that, you will get chemical enhancement. And thirdly, they have also created a device, nano device, graphene nano device, and by applying potential, they actually tuned its Fermi level. When they tuned Fermi level, they got different intensities for different potentials. While they apply plus 150 volt, and they got less intensity compared to minus 150 volt. Actually, what they have done is they have chosen two different potential at the two sides of its Dirac potential. You might have seen the parabola of transfer curve. graphene transistors. So they took two different potential in the two sides of the Dirac point. So they found that while you change the Fermi level of graphene by applying potential, you are actually changing the intensity of Raman signal from a molecule. So that means if the Fermi level is changed, obviously you are changing the charge transfer kinetics. If the Fermi level matches very well with your molecular energy levels, then you will get a better signal. So this is how they have tuned this one, and they proved in all these three mechanisms that graphene is assisting in the enhancement of Raman signal through chemical enhancement. And in summary, I just wanted to touch upon some points like obviously we have discussed a lot, and we have I'm sure I would have convinced you all that CERS centers has potential of detecting and monitoring a single molecule. And not only these three techniques, I have discussed some CERS, Shiners, TERS. Of course, today we have discussed about GERS. These are not the four techniques we have. There are so many techniques emerging with the small modifications in the existing techniques. All these have to be standardized, and when they are standardized, obviously we will have a lot of potential in application side instead of fundamental research. And you can extrapolate its applications to catalysis, sensing, and all these things. You can actually probe a single molecule, and you can study its behavior in simulated conditions over a period of time. And the instrumentation for this CERS analysis is pretty much complicated and sophisticated. You need a bit of sophistication for this analysis, but it has to be simplified. For that, we have to put a lot of effort. The overall, the plasmon-assisted Raman spectroscopy, or which consists of all these CERS, TERS, Shiners, Raman, and so on, everything will open a new era in spectroscopy technical analysis. And thank you for your attention. And I will be happy to answer your questions.
Participants, if there are any queries, please unmute yourself and ask.
Hello, sir.
Yes.
Good morning, sir.
Yeah.
That was a very nice presentation indeed.
Yeah.
Sir, I'm working on thin films. So when I have my film, if I want to do a Raman characterization, Raman spectroscopic characterization, how will I decide which would be better for my film, what I'm looking for? See, I don't know exactly. Like, I have a thin film. I have to decide out of the techniques, whatever you have told, the different SERS, GERS. How do I decide which one is suitable for my film, sir?
Okay, what is your film? Is it metallic film?
It's a metal oxide film, zinc oxide films.
Since it is a metal oxide film, okay, first of all, what you are looking for? If it is a thin film, then obviously you know you will have a lot of Raman signal coming out, so you no need to go for this all these complicated CERS related stuff. Unless otherwise you have a very trace amount of material which you will not think that it will not give you a Raman spectrum, then you have to go for. And if you have metal oxide, generally people tell that metal oxides will give a good Raman spectrum in 488 laser.
Yes.
Laser which is less than 500, but I don't agree with that, because there is nothing, there is no such a hard rule for. Because the Raman spectroscopy is nothing but it's as I already said, it's a row vibronic spectroscopy. So first of all, there should be an electronic transition from between electronic levels. So you should know the band gap. You should know from which electronic level to which electronic level you are going to transfer, and based on that you have to decide your laser. Now, I agree that most of the metal oxides give a good spectrum with 488, but it is there is no hard rule. You should understand the physics behind. I
You
guess
have
I guess I
contributed.
answered your question.
Yes, sir, yes, sir. Thank you so much. Thank you so much. Yes.
Yeah, thank you.
Hello, sir. Good afternoon, sir.
Yes,
Very nice presentation, sir.
thank you, ma'am.
Maximum students have studied the Raman spectroscopy. Maximum the sample studied for Trivandrum Kerala Institute, sir. Any other nearby any Raman spectroscopy instrument available here, sir? Nearby college or university? This facility.
May I know where are you from?
I am Thanjavur, sir.
Okay, you're from Thanjavur. Okay,
My
from
students
Thanjavur.
study in crystal growth and FT Raman analyzed only Trivandrum Kerala Institute only.
You want FT Raman or normal Raman?
FT Raman, sir.
Okay, we have FT Raman facility here. Even our divisional facilities also available.
Yes,
Why do you want to go for FT Raman?
sir, FT Raman, the wavelength Raman spectroscopy, and this is studied only for any other nearby colleges, any available, sir, nearby Trichy or any Chennai.
Trichy,
This
I'm not
facility,
sure.
NMR, EMR, EPR, everything identified, sir. This is a facility available nearby institute, sir.
Yeah, that is what I'm saying. In Karikudi, we have FT Raman. We have in our division, we have FT Raman.
Yes, sir.
But my question is, why you wanted to go for very specific? Because FT Raman is not more common. So people, you will not find quite easily, unless otherwise they have a specific reason they will not keep. And is it a biological sample? Or do you want to analyze?
Nothing, sir. Biological samples, nothing, sir. Only crystal growth, crystal materials, sir. Polycrystalline material.
I see, but in that case, I don't think you have to stick with FT Raman. You can go
When I
for
compare
normal.
this,
You can go with normal Raman. It's you don't need to stick
yes.
with FT Raman, because finding FT Raman is very difficult. You will not see quite frequently in all the institutes. If you want to go for a normal Raman, obviously you can find it in NIT Trichy, and even I
Okay,
think
sir.
even in Bharatdas University.
Yes, sir. Okay, sir. Thank you, sir.
But if
Thank
you
you, sir.
specifically want FT Raman, we have it in our institute.
Okay, sir. Very institute. Okay, sir. Thank you, sir. Thank you for the nice presentation, sir.
Thank you.
Any other queries from participant side?
And I just wanted to give a couple of sentences here, ma'am. May I?
Yes, sir. Yes.
Okay. I think I think this will be a good information for the participant in also. At SICRI, every year we used to get a couple of sessions of students for their master's project, or that includes all MSc, MTech. I think now I don't know that we have MPhil projects, but if there, SICRI is offering MPhil projects also. So you can stay here 3 months to 1 year and do your project using all the facilities. So I just appeal all the participants to look into this opportunity. And we are also happy to receive students having fellowship like CSIR, GATE, or Inspire, and so on. So just look into the SICRI's website and get more information, and encourage your students to apply for SICRI. And that's all. That's all from my side.
Thank you, sir. Thank you.
And thank you very much. Thank you very much, all the participants, for your kind attention. And have a nice day ahead. Thank you.